So Vernon Chitlen from on our video on quantized redshifts asks, is redshift the same in all directions as we look out into space as the Earth goes around in its orbit? Do we see the same redshifts as Earth goes around in its orbital path?
Now, that's a really nice question. So we have to remember when we observe light through our telescope is on the Earth, and the
Mm-hmm.
Earth is moving at roughly, well, there's more than one motion. The Earth is spinning. So
Mm-hmm.
dependent upon where your telescope if is it on the equator, in the tropics, or at the pole,
Mm-hmm.
right? There's motion due to the rotation of the Earth. But the Earth is then orbiting at 30 kilometers per second around the sun. The sun is moving at 240 kilometers per second around the Milky Way. And the Milky Way galaxy is moving at 300 and something kilometers per second. Or was the net motion
Oh, I
600
had
kilometers per second?
600 in mind.
Yeah.
Something like that.
Yeah, something like that. So there's a whole range of motions that an astronomer has to be aware of when they claim to have measured the velocity of something.
Mm-hmm.
So if I take my telescope and I point it towards a star and I get the light from that star and I look at how the lines have shifted due to the Doppler shift, okay? So that tells me the speed of the star. Now I want to know the speed of that star with respect to something. And what I have got in my measurement is the velocity of that star with respect to my telescope at the time of observation.
Yeah.
But if I want to understand how that star is moving in the galaxy, I've got to account for the fact that the Earth is rotating and the et cetera, et cetera, et cetera. So there's a whole bunch of corrections that astronomers have to do. And luckily, we're not the first people to realize this. This is something that goes back to the early days of astronomy, and people
Mm.
have written lots of nice packages that allow us to do the various calibrations to account for the various bits of motion. But that doesn't mean that astronomers don't screw it up sometimes. Now, I believe you've got a little anecdote you could tell us here.
Well, thankfully, I forget what the details are, which anonymizes the anecdote quite nicely. But the story roughly goes that a group of astronomers announced that they had discovered a certain periodic, oscillations in a black hole system. Um, I think it was in a quasar, an active galactic nucleus. It's called the engine of a quasar, and uh, uh, shortly afterwards, they had to retract this result and say, sorry, we didn't actually measure the oscillation of the black hole. What we measured was the orbit of the Earth around the sun. They'd forgotten to do that calculation. Or, maybe they'd done it sort of slightly wrong. There's a bunch of minus signs hanging around that hopefully you've gotten used to. But that sort of thing does happen. One of the things that so in astronomy, you're sort of suspicious of any periodicity, any pattern in your signal that's conveniently 365 days long, because that makes you suspicious that you've measured something about here rather than something about over there.
I think it's worth mentioning here, because it's not just astronomers that worry about this. There's been a great deal of fuss over the last decade or so about the potential detection of dark matter interactions on the
Mm-hmm.
Earth. So this is a famous experiment in the Gran Sasso laboratory in Italy, and it's the Dharma Libra experiment, where they've got a big chunk of crystal, and they are looking for little flashes in that crystal from when possibly dark matter has interacted with the signal, with the material, right? So have we detected dark matter? And they are sort of looking for a yearly signal, because as the Earth goes around the sun and the sun is going around the galaxy, the Earth is on this sort of tilted orbit.
Hmm.
And if there's a background of dark matter, it's like we're traveling through a wind of dark matter, and you'd expect there to be a sort of modulation as we go through. So they've seen
Sometimes you're
this.
going into the wind, and sometimes you're going with the wind.
Yeah,
Yeah.
yeah, yeah. And they've seen something that goes up and down on a yearly timescale. But lots of other things go up and down on a yearly timescale, like the weather.
Yeah.
and the number of cars that drive through the Gran
Yeah.
Sasso Tunnel and everything else, which is why they're building a mirror image of that detector in the Southern Hemisphere in Stawell in Victoria, because if it is a dark matter signal and they do detect it in Stawell and it's in phase, it's doing exactly the same thing at the same
Right.
time of the year, then you can be more confident that it's a dark matter signal. But
Yeah.
if it's out of phase, then you've detected the local weather.
Yeah.
And
This
you've
is the
just,
problem with science. It's
yeah,
so often the two hypotheses, or that you're trying to test. One of them is super exciting, and the other one is really boring, and you
yeah,
just hope it's the exciting one.
yeah, yeah.